enzyme after the type of substrate that it digests, like sucrase, or you can name an enzyme for the reaction they run, like a dehydrogenase, and sometimes it's a combination of both. Lactic acid is the substrate, and the enzyme is going to help us remove a hydrogen from it. Remove a hydrogen from lactic acid. And don't worry about memorizing that. My point is there's lots of different kinds of enzymes based on mode of action. You can sometimes tell hydrolase. So lase, the ACE part is enzyme, and the lyse would be breakdown. So this is a water, a hydrolysis reaction would use a hydrolase, right? A ligase is stitching together. Polymerases, building a polymer. There's just different kinds of enzymes. And your book gets into a big deal about explaining them. Makeup of enzymes. Enzymes are proteins in tertiary structure. This is why I wanted you to do that organic chemistry thing. You need to understand what an enzyme is. An enzyme is a protein in tertiary structure. Tertiary structure means your chain of amino acids twisted, bended, folded, because the amino R groups are attracted or rejected by one another, form into a shape, a very specific shape with little nooks and crannies called active sites. Enzymes are globular. You take the long chain of amino acids and you wad it up. Because they're globular, they're compact and really tiny, so they can travel through your blood and get to where they need to go. They're metabolically active. Some enzymes are strictly protein. Some enzymes also have cofactors or coenzymes that help them do their job. How do they help them do their job? They carry things. Remember, it was in a previous slide. They carry hydrogens and electrons, or they might carry small organic molecules. Cofactors are inorganic ions. They carry hydrogens and electrons, like NAD and FAD, and coenzymes, like coenzyme A, carry small organic molecules like acetyl from glycolysis to Krebs cycle. Then your book gets into a big deal about apoenzymes and holoenzymes, so I put figures to explain that. Some enzymes will have RNA molecules in them. Those are ribozymes. I won't ask you about that. Here's your apoenzyme, the protein part. Here's your cofactor. Here's a coenzyme and an active site. Wow, this enzyme's got it all. So the whole enzyme is the holoenzyme. I just call it an enzyme. I don't call it a holoenzyme. Oopsie, there we go. Again, your book is so detailed. It names every freaking possible cofactor or coenzyme. Okay, if you think of cofactors, there's two kinds of cofactors. So see how it says cofactors? Cofactors can be inorganic ions. Like, what do you see on your vitamin bottle? Iron, chromium, selenium, maybe a little copper, zinc. You ever see those on the back of your vitamin bottle? Yeah. Those are cofactors. They help your enzymes carry electrons and hydrogens and do their job. They're called trace elements because you only need a teeny tiny bit of them. And in fact, if you take too much of them, it can be toxic. Remember, they used heavy metals for drug treatments. They took doses of mercury and arsenic and silver and all kinds of metals. So you do need a little bit, a trace amount, but too much is toxic. In particular, iron. Do not give your child iron supplements. Don't give your child too much iron. If he's got an issue, you need to talk to a doctor about it. Too much iron, and for a kid, too much iron isn't a lot. It's not good for your kid, and they can become deathly ill from too much iron. And also, give them the whole milk. They need fats to develop their brain and nervous system. So sometimes parents think, oh, put my kid on a vegan diet. Probably not a good idea. Unless you do it with the proper education and you know what the kid needs to develop properly.
So that's like one of those nutrition that's the most common deficiency among kids is iron deficiency, either in abundance or not enough of it can cause that.
They might not be getting enough from their food because maybe they're junk food addicts, but if they ate healthy food, they would have enough iron. But it's very dangerous to give iron supplements to your kid without talking to your doctor about it, because iron can be toxic for children in particular because they're so small. I've had iron toxicity myself, and let me tell you, it's no picnic. Because I'm anemic, so my doctor prescribed these iron pills for me to take. I was so sick, somebody actually had to come and get me from work. I couldn't even drive. You get really sick. So kids can get really sick from it. It's dangerous. Okay, how does an enzyme work? Enzymes have active sites, right? Here it shows you a little better drawing. Here's the active site. It's a particular shape. That's where the substrate fits in. Does everybody know what a substrate is? Mm-hmm. Okay, the substrate is the molecule that's going to undergo a reaction and be changed into a product or an end product. Okay? So the substrate is your starter compound. It's going to bind to the enzyme's active site, and it's going to be converted through the reaction into some end product. The substrate must fit the active site of the appropriate enzyme exactly. This is showing you the specificity of enzymes. This is called the lock and key hypothesis. Your textbook author doesn't get into it too much, but remember, the substrate fits into the enzyme like a lock and key. The substrate is actually the key, and the enzyme is the lock. This has to fit exactly in here. What's going to happen is when the substrate finds the enzyme, it will fit in, and then the enzyme will actually bind to it and make the exact shape. If I had something that looked like this, kind of Dracula teeth, huh? If I had this instead of that yellow shape, it wouldn't fit into that enzyme. It's the wrong substrate for that enzyme. Enzymes are specific for the reaction that they run. What is the reaction that they run? Well, it's all about the substrate that's going to be changed. So another way of thinking of it is the enzyme specific for the substrate that fits it. So enzymes are specific to their substrate, which makes them specific to a certain reaction. In a series of metabolic reactions, every different step has to have a different enzyme. And here's another one of those things play. But here, right here, it shows you what's happening. Let's say my substrate is lactose, and my enzyme is lactase. I have a molecule of glucose and a molecule of galactose. Well, actually, that's a bad example because they're the same shape, so let me change it. Let's say my enzyme is maltase, and this is a molecule of glucose and a molecule of glucose. The enzyme binds to the disaccharide. See how it fits exactly? The enzyme enables the reaction to run. The reaction splits my glucose monomers apart. So it splits my maltose into 2 glucose. What kind of a reaction is that right there? I have to put water in there, not showing that. It's a hydrolysis. I'm splitting a disaccharide into 2 monosaccharides. So they don't show it, but water must have to enter this reaction. It's a hydrolysis reaction. And what do I end up with? My enzyme is unchanged. My substrate got changed into a product, into two products, but my enzyme is the same. So enzymes are reusable, not forever. I mean, it's a molecule. It's going to eventually wear out, break down, and your body's going to make new ones. But theoretically, enzymes are reusable because they're not changed by the reaction. And that's what a catalyst is. It enhances the reaction, allows the reaction to run. The substrate's going to be converted into product, but the enzyme itself is unchanged by the reaction. So the enzyme is therefore reusable. And remember, enzymes are proteins in tertiary structure. Metabolism of lactose into glucose into lactose. Sometimes I draw that stuff on the board. We don't have time this summer. All right. Things that affect enzyme activity. Have you heard of denaturation? Right. So the influence of body heat is one thing that can affect your enzymes. Temperature, your body heat. Also, if you cook an egg, when you open your egg, it's kind of gooey, you know? And you put it in the frying pan and they say this is your brain on drugs. Anybody remember that commercial? Mm-hmm. Okay, so now they have a new one. It's bacon. What do you say about the bacon? I don't remember. I forget. Oh, it's about sunscreen, I think. Like this is your skin out in the sun, the bacon sizzling. Anyways, so the egg is gooey. That's the natural state for the proteins of the egg, which is why bodybuilders suck raw eggs, because the protein's in its natural state. It's actually theoretically better.